Question 21, April 2025, Onramps Physics. And this one, the interior of a refrigerator has a surface area of 6 square meters. It is insulated by a 1.7 centimeter thick material. I'm going to have to convert that to meters. That's divide by 100, 10, 100, 0.017 meters. Everything has to be meters. That has a thermal conductivity of 0.0324 joules per meter seconds Kelvin. Okay, that's good. The ratio of the heat extracted from the interior to the work done by the motor is 8% of the theoretical maximum. So I multiply whatever theoretical maximum by 0.08. The temperature of the room is 36.9 Celsius, and the temperature inside is 7.9. Now, in these, there's a difference of temperature. Difference in degrees Celsius is the same as difference in degrees Kelvin. So if I add 273.15, the difference is still going to be the same. So I'm going to put here the delta T equals 36.9 minus 7.9. 36 minus 7 is 29. I better put it over here because I think I need the room over there. Let me move this over because I'm leaking into what I have to write on the other side. So the temperature difference is 29. And I'm looking at my thing here, 29, Ka delta T, T low. Oh, okay, so I'm going to see how this, I have to find the coefficient of performance, and it's the low temperature divided by the difference. Well, the low temperature I'm going to need in Celsius, the difference is 29, or Kelvins rather. The difference is 29 whether it's Celsius or Kelvin. So I can just put that 29 down there, and 29 will also be here. All right, so what is the low temperature? 7.9 plus 273.15 Kelvin, or 15 to get to Kelvin. 11, 7, 8. So 281.05 Kelvin is the low temperature. That's the temperature inside the refrigerator. So I'm going to have to find the amount of heat that I have to pump out of the refrigerator. And the more, whatever the temperature is inside the refrigerator, the difference between that and the temperature outside, so on a really hot day, the refrigerator has to work harder. So I have to find the amount of heat that needs to be pumped out of the refrigerator. That's the amount of heat that leaks into it through the insulation. If that was 0, I'd never have to pump. Your refrigerator would never have to turn on because it would be 100% efficient. No heat would leak into it, would get into it after it got cool. But that's not how the real world works. This one is 80% efficient. All right, so this is what I'm ultimately going to have to do. I'm going to have to find the coefficient of performance is the heat that needs to be pumped out, the QL, or the heat that gets in, that leaks in, divided by the work that I have to do. Determine the power required to run the compressor. How much work do I have to put in this thing? And it's going to be in watts. All right, so the work in watts is going to be the heat that I need to pump out divided by the coefficient of performance, the actual coefficient of performance. So I'll put a little sub A there. All right, how do I find the heat that gets into the system? The heat that I have to pump out is the heat that gets in, is K, that thermal conductivity of the insulating material, times the area, surface area of the insulating material, times the temperature difference, divided by the thickness of the insulation. So I've got 0.00324. And I want everything in meters, seconds, kilograms, joules, pascals, etc. So I'm good here. It's joules, meters, second, kelvins, and kelvins. 0.0324 times the surface area, which is 6 square meters, times the temperature difference, which is 29. And I'm going to divide that by the thickness, but it's got to be in meters, 1000, 0.017. And I'm going to use that exact value because I do it in Desmos, but I will look up that value, and let me find where I have Desmos here. Let's see, do I have that anywhere? Yeah, Yes, I guess I have it here. I got to get rid of that part. Okay, so 0.0324 times 6 times 29 divided by 0.017 is approximately 331.624. 331.624 watts, approximately. I'm going to use the exact calculation. Now, I have to find the coefficient of performance for the ideal situation. For the ideal situation, it's going to be the low temperature in Kelvin, 281.05, divided by the temperature difference, the high temperature minus the low temperature. The temperature outside the refrigerator minus the temperature inside. So 281.05 divided by 29. 281.05 divided by 29. That comes out to approximately 9.69. And then I have to multiply that to get the actual coefficient of performance. I have to multiply that by 0.08. So that times 0.08. And I'm just going to throw that right here into Desmos. Times 0.08. I get 0.775. So it's approximate, when I multiply it by 0.8, approximately 0.775. That's this, approximately 0.775. All right, so now I have to do my final calculation. The work in is that energy, 331.624, or that top calculation in Desmos, divided by approximately 0.775, was it? It looks like a 3 for some reason. Or this exact thing. So I'm just going to take this, boom, divide, paste it, and I get 427. The final answer is approximately 427.73. It's this value divided by this value, except I use the exact values. It comes out to about 427.73 watts.